Hello, class. This is Lab 5, which is a torsion testing lab. I want to sort of get that off there. And I looked around for a simulator and for virtual labs or whatever. I couldn't really find one, but what I did find was more or less an ad for some virtual strength and materials labs. And I can certainly see why Wentworth would not have gone to the point of buying all these virtual labs for the 1 or 2 semesters that we're off, because they're very expensive. But this is a demonstration. So what I'd like to do is I'd like to share this screen with you. Just a second. There you go. This is a YouTube demonstration. I'm going to bring it all the way back to the beginning and just sort of preface this a little bit. This is a sort of a preview type of a demonstration of a torsion lab for virtual laboratories, which is a company that sells these so that you don't have to buy the large equipment, which we do have at Wentworth. And I would have done this on those if I could go into Wentworth with it, which I can't. So what I want to do is I want to play this for you first so that you can sort of see what's going on. I'm going to expand it into full screen, and I want you to sort of look at it. It's very similar to the torsion testing machines that we have in the back of the strength and materials lab. Now, the first thing you notice is that there's a black line that is drawn on the tensile specimen. Now, we're going to assume that that tensile specimen is 4 inches long, right? And as you can see, we're in the elastic part of the expansion now. Now I'm going to hold that. I'm going to let it go all the way up into the full expansion, sort of pulling off. Then it's going to pull in. Now look at this graph printout that we have. You can see a couple things, and these are the numbers that I want you to use when you're working this out. It has extended 5.33. Now you can see that that's actually probably a little bit far, because there is a little expansion here at the beginning where it's just taking the slack out. So the 0, probably isn't exactly right. However, I'm going to use these things. So we're at 59 Newton meters applied torque. And at that 59 Newton meters, I'm going to say that we're at about 5.3 degrees. Now, of course, we cannot use degrees in engineering calculations, can we? Because engineering calculations use radians. And so we have to turn those degrees into radians, and I'm going to let you do that using the conversion factor that there's 2 pi radians in 360 degrees, right? 2 pi radians in 360 degrees. Now, we have 2 different equations. We have that the angle of inclination, which would be in radians, is equal to the torque applied times the length of the specimen, and I'm going to say the length of that specimen is 4 inches, and you can approximate that in the SI system with approximately 25.4 millimeters to an inch. Let's say it's 25 millimeters to an inch. 4 times 25 is 100, so it would be about 0.1 meters, wouldn't it? Right? 100 millimeters is about 0.1 meters. So the length is going to be about 0.1 meters. The torque is going to be about 59 Newton meters. The angle, I'm going to let you do that, is 5.3 degrees, or whatever that is in radians. And so we've got an equation, theta equals TL over JG. And we're looking right at this point, right at where we end the linear relationship or the elastic relationship of that torsion rod. So theta equals TL over JG. I'm going to give you G as well. G, the modulus of rigidity for iron, is 66 gigapascals. So we have a few different things now. We've got 66 gigapascals is the modulus of rigidity. We know that the equation is theta equals TL over JG. So what are we looking for? The only thing that we don't know is J. So in that equation, theta equals TL over JG. I'm not going to write that down because this should be committed to memory by now with all of the lectures and all of the reading that you've done. Theta equals TL over JG, and you're trying to find J. So J then is going to be equal to TL over theta G, isn't it? You're going to find J, and you know that J is pi times r to the fourth divided by 2, right? The polar moment of inertia of a circular cross-section is pi r to the fourth divided by 2. So what you have to find for your lab is what is the polar moment of inertia. So let's do this. A, what is the polar moment of inertia of that tensile specimen? That's the first thing. B, trying to make this as clear as possible. And this should only be 5 minutes, 5-minute lab really, maybe 15-minute lab. So once you know J, and you know that J is pi r to the fourth over 2, I want you to find R. What is the radius of that tensile specimen? Remember, L is approximately 4 inches. I'm going to say use 0.1 meter for L in that equation. Theta equals TL over JG. I think I've said that about 25 times now. So, but I know that you've all committed that to memory anyway. So A, you're going to find the polar moment of inertia. B, you're going to find out what the radius is. And then I want you to find what the maximum shear stress is, because the maximum shear stress at the very end of that linear line that you see on the screen is going to be equal to the torsion times the radius, which you found in part B, and then divided by the polar moment of inertia, which you found in part A. And that's going to give you, in megapascals, what the maximum shear stress is for iron just before it goes from the elastic region to the plastic region, right? So that's the maximum shear stress that you would have for iron. Those are the 3 things that I want you to do. Find the polar moment of inertia using theta max, or theta equals TL over JG. And then from that, you can easily find out what R is, and then plug those back into this maximum shear stress equation. Maximum shear stress equals TR over J to give me what the maximum shear stress is in the elastic region before it goes from elastic to plastic of iron. Now let's finish watching this video. All right, you can see now that this is extending into the plastic region, which is something we're not all that concerned about. And it's going to keep twisting and twisting and twisting because, thank God, ductile iron twists and twists and twists. Otherwise, if we were involved in a car accident, that front bumper and front fender and stuff would not keep collapsing. Remember the straight line that we had on this, and you can see that it's twisting, twisting, twisting. That's quite far. When we look at the break and back at the graph, there you go. Now it broke virtually, and now we're going to go back and look at the graph, and you can see how much that's twisted around, about 6 times, right? If you go back to the graph and you look at the graph, I'm just going to hold that for a second. you look at that graph, you can see that the elastic region is almost a vertical line right now, and that the plastic region has a huge amount of ductility to it before that torsion rod finally breaks. All right, so that's what I want you to do for Lab 5. I'm going to stop sharing right now. I'm back here. I don't know, that's a very strange picture I have of me, but whatever. I'm going to stop this, and this is going to become Lab 5. I'm going to do a Lab 6 on flexure. All right, see you then.